Hello and welcome to online lecture number 6 for Chemistry 112 during the spring semester of 2020. In this lesson, we're still in chapter 16, and we're going to continue on with what's called the third law of thermodynamics. From last lesson, we have this equation, one of the most important equations from the entire chapter, which relates to change in Gibbs free energy, which is what we use to determine whether or not a process is spontaneous or is non-spontaneous, to the change in enthalpy, the temperature, and the change in entropy. So in order to calculate delta G, and or actually apply a number here, we either need to be given or be able to calculate delta H, and we're able to do so from what we learned in Chemistry 1, as well as either be given or be able to calculate delta S. But to calculate delta S is a difference entropy between the products and the reactants, so we have to be able to quantify what we mean by the entropy of a particular state of a substance. But if entropy is disorder, entropy is a measure of disorder, a measure of randomness, how do we quantify that? We've already seen how the entropy can be affected by the physical state of a substance. Gases have higher entropy than liquids, which have higher entropy than solids. The number of particles, the greater the number of particles, the greater the entropy of a state, as well as the volume of space. So everything else being equal, the larger the volume of space available for that particular state of matter, the larger the entropy is going to be. Well, we can quantify this using what's called the third law of thermodynamics. But before we get there, though, we want to consider at least one more factor that does affect the entropy of a particular state of matter, and that is the temperature. So the temperature, even for a given substance, the temperature will affect the entropy of a substance. So consider our pictures of a gas, for example. At relatively low temperature, you have the particles bouncing around in their container, but because it's at low temperature, they're bouncing around at relatively low speed. Recall that thermometers are molecular speedometers. Whereas at higher temperature, those same number of particles, for example, are bouncing around at higher on average speed than they were at the lower temperature. So that's the difference. That's what the temperature is reflecting, is that at higher temperature, the molecules on average are moving with higher kinetic energy, higher speed than they would be at lower temperatures. But there's another difference here. And that difference is not only in their average speeds, as we can see here, that at lower temperature, on average, the kinetic energy is lower than that of the same substance at higher temperature. But also notice that not only does the average change, but also the distribution of these kinetic energies, the distributions of these speeds also changes. In particular, at higher temperature, this distribution of kinetic energy increases. This curve gets wider. So everything else being equal, at a higher temperature, not only do molecules on average are moving faster, but there's a greater distribution of how fast they are moving, a greater randomness in how fast they're moving, therefore a greater entropy. So everything else being equal, increasing the temperature of a substance will increase the entropy of that substance. So keeping that kind of idea in mind, when we want to be able to try to quantify this idea of entropy, quantify disorder, we can do so by imagining that if increase in temperature, increase in entropy of a substance, imagine the lowest possible temperature. So the lowest possible temperature would be 0 Kelvin, absolute zero. And if we had a perfectly ordered substance where all the molecules and atoms that make up the substance are perfectly aligned with one another, it's at 0 Kelvin, so there's absolutely no movement of that. The third law of thermodynamics then says that for that particular state, so a perfect crystal at 0 Kelvin, there's only one microstate, there's only one way that can possibly happen. And if the number of microstates is 1, because entropy equals Boltzmann's constant, natural log W, because W is 1, natural log of 1 is 0. So as a result, the third law of thermodynamics defines the entropy of that particular perfect crystal at 0 Kelvin as exactly 0. As a result, then all the other entropy values that we'll use to quantify delta S are then all positive because they're all relative to this perfect crystal at 0 Kelvin. So all other substances, regardless of their physical state, or number of particles, or volume of space, or temperature, all those entropy values will be positive and they're all relative to, by definition, this picture, which has an entropy of exactly 0. And so we can see how the temperature does affect the entropy. We've already considered how going from the solid state to the liquid state to the gaseous state, there's an increase in entropy. But even within the solid state, notice that going from a very, very low temperature up into the melting point, as the temperature increases, the entropy also increases. Likewise, the liquid, we see the temperature increase, and as well as the gas, the temperature also increases. The entropy increases as the temperature increases. So we see the biggest jumps as you go from the solid state to the liquid state, and especially the liquid state to the gaseous state. But even within the same physical state, if I continue to heat my gas beyond its boiling point, its entropy will continue to increase because I'm increasing the randomness of those kinetic energies, the distribution of those kinetic energies. So this third law of thermodynamics then will help us establish what we mean by the entropy of any other substance. So we've already seen how the entropy of a substance depends upon its physical state, depends upon its temperature, depends upon the pressure or volume, if it's a gaseous substance especially, as well as depends upon the amount of the substance. So because all of these factors and more will influence or otherwise determine the entropy of a substance, if I want to make sure that when I'm considering entropy or if I'm defining entropy of a substance, I'm defining it the same way that everyone else in the world would, I want to make sure that my values are not different from how they measure their values. So as a result, by convention, there's what's called the standard molar entropy. And it's the S for entropy and then a little degree sign in case it's a standard state, which means that this is the entropy of the substance, specifically 1 mole to molar entropy of 1 mole of a pure substance at 1 atmospheric pressure and at a given temperature. And usually it's room temperature, so usually 25 degrees Celsius. In our textbook, we have Appendix G, which gives us the standard molar entropies for a large variety of substances. So from that appendix, we can take a look at a couple examples, just to kind of reiterate what we've already talked about in terms of factors that do influence the entropy of a substance. Notice that all these are the same temperature, so we eliminated the temperature effect. The gases, carbon dioxide, hydrogen, they have much higher entropy than the liquids and certainly much higher entropy than the solids. Even within the two gases, carbon dioxide versus hydrogen, carbon dioxide's entropy, molar entropy, is a lot higher because even though they're both gases at the same temperature, carbon dioxide's entropy is higher because carbon dioxide is a more complicated molecule. It's a more massive molecule and it has more chemical bonds. So even comparing two substances in the same physical state, generally speaking, the more complicated the molecule is, the more chemical bonds that are present, the more massive it is, that's a substance that's likely to have the higher molar entropy. Liquid water has kind of a moderate entropy, and with our solids, they have roughly low entropies. Notice that at the very bottom, we have carbon, 2 forms of carbon. Carbon in the diamond form has an entropy of 2.4, whereas carbon in the graphite form has an entropy of 5.7. And we introduced this chapter with kind of an interesting fact that the conversion of carbon in the diamond form to graphite is a spontaneous process. Very, very slow, but it is spontaneous. And one of the reasons why is because the entropy of graphite is higher than the entropy of diamond form. So as a result, the change from carbon in diamond form to carbon in the graphite form has a positive delta S. And we can see that if we look at the structures of these two forms of carbon. In the diamond form, it's just pure carbon atoms, but they're all tetrahedrally bonded to one another, so fairly rigid structure, so therefore a very low entropy. Whereas in the graphite form, carbon exists as sheets. And so you have one sheet of graphite loosely bound to another sheet of graphite, loosely bound to another sheet of graphite. So yes, these sheets are fairly stable, but one sheet can slide past another sheet. And so that movement, a possible movement of one sheet over another sheet, is essentially what we're doing when we're writing with a number 2 pencil is we're rubbing a sheet of graphite off of our pencils onto the paper. That additional movement gives rise to additional disorder, and so therefore higher entropy. So this conversion from this low entropy state to a high entropy state is going to be spontaneous. But as we said before, very fortunately, very slow. So we can use these numbers then, as we'll see in the next slide, to calculate for any particular process, to calculate delta S. And delta S then will be one factor, which is going to help us ultimately calculate delta G, and which helps us determine whether the process is spontaneous or non-spontaneous. And then probably next lesson, we'll talk about what we mean by the actual, not only the sign delta G, which we've already talked about, but also the magnitude of delta G. So to calculate the standard entropy of a reaction, the delta S under standard conditions of a reaction, it's equal to the sum of the number of moles of the products times their respective molar entropies minus the sum of the number of moles of reactants times their respective molar entropies. So it's just a difference between the total amount of entropy of the products and the total amount of entropy of the reactants. So we'll end this lesson with a kind of simple example. In the next lesson, we'll do a couple more examples of calculating delta S as part of a larger calculation. So we have N2O4 going to 2NO2, both in the gaseous phase, but we notice that going from one molecule of N2O4 to 2 molecules of NO2, we're doubling the number of molecules. So it's very likely, and as we'll see, this process has a positive delta S. But if we actually want to assign a number to it, how positive, then we actually need to know the respective molar entropies of the products as well as the reactants. So the molar entropy of N2O4 is 304.2 joules per mole Kelvin, and the molar entropy of NO2 is 240.0 joules per mole Kelvin. Notice that N2O4 has a higher molar entropy because it's more massive, it's more complicated, more chemical bonds compared to the simpler NO2 molecule. So we want to calculate delta S for this particular process. We have our respective molar entropies. So all we need to do is just apply the equation. So we have delta S of this process, which we expect to be positive, is equal to the sum of the number of moles of each product times the respective molar entropy. So this would be for each product, the respective stoichiometric coefficient. So we have 2 moles of NO2 times its molar entropy, joules per mole Kelvin, minus the sum of the number of moles of reactants times their respective molar entropies. So we have 1 mole of reactant, so it's going to be 1 mole of reactant times its respective molar entropy, which is 304.2 joules per mole Kelvin. So then our delta S is equal to 2 times 240. So we have 480 joules per Kelvin. That's the total entropy of the products of the 2 moles of the NO2 molecules in this case, minus 304.2 joules per Kelvin, which is the total entropy of the reactants. So finally, our delta S value would be 480 minus 304.2. 480 minus 304.2 gives us a value of a positive 175.8 as our delta S. So as expected, as predicted, this particular process does have a positive delta S, and if we know the molar entropies, we can actually calculate it as exactly positive 175.8 joules per Kelvin. And as we mentioned at the beginning of the lesson, we can then use this number as part of this equation, for example, to calculate the delta G of that process, and then decide whether at a given temperature, whether that process is spontaneous or is not spontaneous.